evening for me is Sunday evening, the Monday before you're watching this video. And I would like to welcome you to 4.9, combining random variables. And Mr. Bobby and I are going to split the load a little bit. So you're going to see a little bit of just me and a little bit of just him and maybe a little of us together again before it's all said and done in this unit. Okay? So today we have a couple of big learning objectives, and get your notes ready to go because it's kind of a toughy section, and I'm going to try to power through it as fast as I can, but there's a lot of content. Okay, so let's get ready to rumble. We're going to do a couple of things. We're going to calculate parameters for linear combinations of random variables, which sounds crazy hard, but it's not. And then we're going to describe the effects of linear transformations. And so our learning objectives, I'm going to shrink me because I'm causing issues here. Our learning objectives here, and I can't Bobby eyes them, but I'll talk through them quickly, but we're going to circle back just like always. Okay, so for any random variables x and y and real numbers a and b, the mean of a times x plus b times y is just a times the mean of x plus b times the mean of y. So you can just straight multiply those means and add them together. Okay. Two random variables are independent if knowing information about one of them does not change the probability distribution of the other. So we've talked about this in previous videos. If we say the probability of A given B is still the probability of A, then those two events are independent of each other. Okay. And for independent random variable x and y, so independent here, that's why we brought that back. Real number a and b, the mean is the mean, and the variance is the variance, but standard deviation is not, and we're gonna come back to that, like what you do when it's, hold on, there's a train coming, I'm gonna pause us. Okay, loud train. Barking dog. Just change of location was necessary. Okay, we're going to come back to that concept of standard deviation, but know that the standard deviation can act extra, and so you always want to think about when does standard deviation go wonky, okay? For y is equal to a plus bx, the probability distribution of the transformed random variable y has the same shape as the probability distribution of x, so long as a is greater than 0 and b is greater than 0. The mean of y is going to be a plus b times mu, and the standard deviation is going to be the absolute value of b times the standard deviation of x. What? Okay, so let me show you a picture of that last thing because it's so confusing sounding, but I think if you know anything about parabolas, I can make this make sense to you, okay? So let's say we've got a normal distribution, and we've got, you know, all these dots making this dot plot. We've got a normal distribution, and what we want to do is we're going to add a 6 to every number in that distribution. So like a lot of you did a project, when you did your project, your Snapchat or Insta project, where you had to ask the question on how many pets do you have, like half of you, I think. And so it's like if everybody said 6 more, like than they actually said, right? So if everybody had an additional 6 animals in their home, what would we expect to happen to the distribution? Would we expect mean to change? Would we expect standard deviation to change? Would we expect range to change? Like, what do we expect to change if we add 6 more animals to everybody's household? Okay, so I think you can kind of picture this, like if I have 10 animals, I now have 16. If I have 8 animals, I now have, what are we doing? Adding 6. I now have 14 animals, and so on and so forth, right? So I just, like, literally, I'm going to take this whole thing and shift it up 6. And so now its mean is 16. The mean number of animals would be 16. It didn't get any wider, though, right? We didn't say some got more, some got less. We didn't say anything about the range because it's being added to everybody. So think about a parabola, right? Think about what you learned in Algebra 2 or Pre-Cal or whatever the last class you had where you had to talk about parabolas. How if you add outside of the function, outside of x squared, you shift that function up and down, and if you add inside, you shift that function left and right, depending if it's positive or negative. Same thing's happening here with the normal distribution. If I add, it's shifting. All I'm doing is shifting, not changing shape or anything like that, okay? So that's addition. But if we multiply a distribution, so think about what's gonna happen to a parabola when I multiply it. I get that vertical stretch and shrink, right? Same thing is gonna happen here, okay? So now I'm gonna take everybody's pet, and I'm gonna say, oh, they have twice as many pets. We're gonna add twice as many pets into their home. So if they have no pets, they're still gonna have no pets. If they have one pet, now they're gonna have two. But if they have 6 pets, now they're gonna have 12. So you see that the distribution or the increase is not the same for everybody because we're doubling. And so what happens is we stretch out, right? We horizontally stretch out that distribution. And now our mean is at 8. And you can see our range is wider, our standard deviation is wider, right? It's really stretching out that curve, probably no longer normal. And so we gotta think about it like this. Now, remember, we're talking about random variables, right? So the same thing is gonna happen. If I'm looking for an expected value, and remember, expected value is just the mean of random variables, and I'm saying, okay, twice as much. Well, the mean is twice as much. The standard deviation is twice as much. But the variance is not twice as much, okay? So in this case, when I multiply times 2, if my standard deviation gets multiplied by 2, so stretching it out twice as big, stretching out that standard deviation twice as much, I think about squaring this, and remember, squaring the standard deviation is how I get to the variance. Then I'm squaring, the times 2 of the standard deviation, and it's becoming 4. If this had said multiply the random variable times 3, then the variance would be changed times 9. The variance is going to be changed by the square of the multiplier, okay? So the variance, when I'm multiplying, acts funky. Okay, so thinking about it like this, when multiplying or dividing a random variable by a constant, mu is multiplied or divided by that constant. Standard deviation. So mean, standard deviation, just multiply or divide by that constant. But the variance is squared. So it's multiplied by the constant squared. But the shape is going to remain the same. Okay, if it's normal, it's going to stay normal, that kind of thing. Maybe not perfectly normal, but you know. But if it's like skewed left, it's going to stay skewed left. Skewed right, it's going to stay skewed right, that kind of thing. Okay, so think about this problem. You move me. Pete's Jeep tours offer a popular half-day trip into tourist area. Imagine like the most beautiful place you can imagine right now. We all have travel envy because we're stuck at home. But imagine you're at a tourist spot. It's a resort. It's beautiful. There's beaches. There's yummy food. Anyway, I'm getting sidetracked. There must be at least 2 passengers for the trip to run. The vehicle will hold up to 6 passengers. Define X as the number of passengers on the trip. Sorry, I got cut off there. So let's say we got passengers has to be 2, no more than 6. So 2, 3, 4, 5, and 6. That's our possibilities. Well, let's say the probability of just 2 people riding is 0.15. And we can go up, all the way to the probability of 6 people riding, okay? And just to double check that we've got a good distribution here, I could add them all up and confirm that I actually have a probability of 1 or 100%. So I've considered 100% of the scenario. And so that would be what, 40, 75, 95, 100, so we're good there. And we could graph this as a histogram. It would look something like this, right? So the probability of 2, 3, 4, 5 looks approximately symmetric. Looks like the mean is around 4. Looks like it's got a range of 6 minus 2, which is 4. If we were asked to describe the distribution, right? Remember, we got custom BS, center, anything unusual, nah, shape, approximately normal, spread, that kind of thing. Okay. And so let's say I tell you that the mean is 3.75 and the standard deviation is 1.090. Now I can be more specific in my explanation now that I have more information. I can say, okay, the mean is actually 3.75, and I want to be specific. So I would say the mean is 3.75 passengers in the Jeep with a standard deviation of 1.090 passengers, right? So now I can be more specific with my center and my spread. All right, so let's say that Pete is going to charge $150 per passenger. So Pete's going to, now we've got this distribution, but he's going to charge $150 per passenger. The random variable C describes the amount Pete collects on a randomly selected day. So what I'm going to do is I'm going to take my number of passengers, 2, 3, 4, 5, 6, and I'm going to multiply them by that $150 per passenger. So 2 times 150 will be 300. You can hear my dog. 3 times 150 will be 450, and so on and so forth, right? So I'm just multiplying the number of passengers by how much per passenger. But the probability of that number of passengers doesn't change. So the probability of that much money collected doesn't change, okay? So the distribution is going to look something like this. Now, it's kind of important that we just look at this, right? So we've got this distribution that is now, look how the y-axis has changed. Not at all, right? Remember we said the probability doesn't change. But my x-axis does change because it's going from number of passengers to money collected, but I'm still just have the same place, right? Because it's just 2 times 150, which is 300. So now the probability is the same. It's just the x-axis has changed times that amount, okay? So think about taking this bar graph, and what we've done is we've just shifted it way up the number line, way up the x-axis, all the way up to the 300 to 900 range, okay? And now the mean is about 562.50, which is 3.75 times 150. And the standard deviation is 163.50, so 1.090 times 150, okay? So what happened if I wanted to compare? Remember, use your words. So the center is increased from 3.75 times 150 to 562.50. Standard deviation, you would say something similar. Shape is the same, right? Shape does not change. So just kind of, you know, talking through this stuff of like, what does it mean when we say shape doesn't change, right? Because that makes sense because the distribution itself doesn't change, just what we're talking about, okay? All right, we're still on Jeep stores, and I'm gonna pause us for just a second again. Hang on. Okay, so sorry, I had to fix the screen here, and so we're still talking about the tours, right? We just talked about, okay, how much is Pete making? 300, 450, 600, 750, 900, depending on how many people he's got going here. And we know what the mean is. We know what the graph looks like. But let's say that it's going to cost Pete $100 per trip to buy permits, gas, and a ferry pass. The random variable V is describing the profit he's going to make now. So there's a difference between like how much money's coming in and how much I'm actually profiting from that because we've got cost. So for every single person, it's going to cost him $100. So now we're saying, okay, this, you know, each one increases by one person, right? So this is, and if you need to back up, that's okay. We've got distribution of 2 passengers here. And so what we end up with here is kind of subtracting $100 and across the board, right? And so, because we're talking about permits, gas, and ferry, and I think I said per person, but now that I'm reading this, it's not per person, it's per trip, right? Per trip, sorry. So just minus 100 for each one. So we talked about multiplying. So now we're talking about subtracting, and I want you to really think about what we talked about with the parabola, right? With multiplying, we change shape. We change shape, so we should expect standard deviation to change. We should expect mean to change. When we subtract, we're just shifting. We're shifting. And so what am I expecting to see happen? Well, I'm expecting to shift the whole thing down 1. And now I've got a mean of 462 and a mean of 163.50. I mean, a standard deviation. So look what happened here. The mean subtracted by 100, but the standard deviation was unchanged. And I didn't highlight this earlier, so let me make sure that I do that. I said it, but I didn't show you. So this range over here is 4. But if I think about this range here, this range is what? 600. So you can see it's spread itself out, shifting down, spreading out, shifting down, spreading out. But this, when I compare these two graphs, my spread is, I felt blind when I'm looking at this, 600, and my standard deviation is 600. So standard deviation, nope, get my words right. In class, y'all be yelling at me. Ms. Young, what you doing? Your standard deviation is 163.50 here, right? And it remains 163.50. Your range, and range is often easier to see. They're both types of spread. So we've got a spread or a range of, and remember, we're not talking about a range. Like we wouldn't say 300 to 900. We'd say a range of 600 because we'd subtract those two numbers. So 600 and 600 in both. So if we custom BS in comparison here, you know, we've reduced the center by 100. The shape has remained the same, but the standard deviation has also remained the same in this one, okay? All right, so let's look at another one. I gotta move stuff. So it says, let X be the number of gallons required to fill a propane tank. Suppose that the mean and standard deviation is 318 gallons and 42 gallons respectively. The company is considering the pricing model of a service charge of $50 plus $150 per gallon. Let Y be the random variable of the amount billed. What is the mean and standard deviation for the amount billed? Okay, so we're getting into this sort of concept of linearity. You've got one thing that adds and subtracts and one thing that multiplies, okay? So when you think about how you're changing things, the service charge is a flat fee. The service charge is a flat fee. So it's like an addition or subtraction. And then you see plus 180 per gallon. Per gallon is a rate, meaning it's a multiplier. Think about like slope, right? Flat fee plus rate, that should remind you of a linear function. You should be thinking, y equals mx plus b. Let me write an equation. Y equals 50 plus 100 or 1.8 x, or g for gallon, okay? So how does that affect mean and standard deviation? That's the next question. How does it affect mean and standard deviation? Well, think about it like this. If I write my equation y equals 50 plus 1.8x, what happens to my mean? Well, my mean is affected by both. Remember, if I'm shifting or I'm stretching, no matter what, that mean is changed by both variables, okay? So I can literally just plug my mean in, multiply it and add to it, and my mean changes to 622.40, okay? My standard deviation though, my standard deviation is not affected by an addition. It is not affected by addition or subtraction, right? Because the addition or subtraction is going to take that same shape and move it. But my multiplier is going to take that shape, spread it out, okay? So when I go here to find standard deviation, I multiply 1.8 or the absolute value of 1.8 because if it were negative, you wouldn't want to multiply by a negative here. Times that standard deviation of 42, and that gives you 75.6. And then be specific. So my mean is now $622.40, and my standard deviation is $75, okay? So circling back one more time, when I'm altering my mean by an adder and a multiplier, both change the mean, both addition and multiplication, okay? Multiply first, then add. But standard deviation is only affected by the multiplier. So I would not add 50 to my standard deviation. I would only multiply, Okay, moving on, moving on. So far, we have looked at single random variables. Most of the time, or a lot of the times though, we want to talk about how random variables interact with each other. Okay, so if I want to add them or subtract them. So let's investigate the result of adding and subtracting random variables. Let X equal the number of passengers on a randomly selected trip with Pete's Jeep Tours, and Y the number of passengers on a randomly selected trip with Aaron's Alaska Adventures. I've been to Alaska. It's beautiful. I recommend it. So we're going to define T as X plus Y. Okay. So we are going to add the number of passengers on Pete's to the number of passengers on Aaron's. Okay, so here's the information below of the probability and the distribution of the two. Okay, so here's what happens. I end up with mean and standard deviation. We already looked at this one. Aaron's mean and standard deviation look like this. She's right skewed with a mean of 3.10 passengers and a standard deviation of 0.943 passengers. Okay, and so the question is like, if I want to find the mean and standard deviation of the sum of these two situations or the sum of these two tours, what does it look like? Okay, so what it turns out is that I can just actually add the means together and I will get the mean. Okay, I will get the mean. So I could go through this with you, but I'm saving you a lot of heartache. So we could sit here and do expected value, plus expected values, and then find the mean of all of that. But it turns out just going to be the mean. Just add the two means together. Okay. But standard deviation does not work the way we want it to. Okay. So let's say we do all the math. Okay. So this is what happens when we combine X and Y and we do the long standard deviation formula, which you've seen me do before. And we know that the mean is 6.85. And so we go and we find variance, which is our T minus our mean each time. Okay. So we go through this process and then times the probability here for every single one of them. 4 minus 6.85 squared times the probability of that particular thing happening. Okay, through all of them. And we get the variance to be 2.0775. Okay, now I'm talking variance here because, and maybe I should have shown you, how do I find the mean of this? Well, you would just do, probability times, you would sit here and multiply and add up all of those things. Okay, if you've forgotten. So now I'm going through the process and I get to this point and I'm like, okay, I'm going to take the square root of this variance and that's going to give me standard deviation and it's going to be right. But unfortunately, it's wrong. It's not the way that it works. But if I think about the standard deviation of X and the standard deviation of Y, I don't remember the people's names now because I'm being an airhead. And I think about those standard deviations, I try to add them together. I'm not going to get the square root of this, okay? But the variance of X is 1.187, and the variance of Y is 0.89. And if I add these two together, they do match the variance of X plus Y, okay? They add. So what happens here is if you're given standard deviation, you can't use it. Can't add standard deviation plus standard deviation and get standard deviation for your sum and difference of random variables. You have to go to the variance. Okay, you have to go to the variance. So here's, if we're generalizing, here's what it looks like. If I want to add two random variables together, I can literally just add the means, and that's the mean of the combination. Okay. So Pete's mean 3.75, Aaron's mean 3.10, or you say expected value. The expected value of Pete plus Aaron is mean plus mean of Pete plus Aaron. Okay, super easy, super exactly what you expect it to be. What about variance and standard deviation? Well, standard deviation does not work that way, okay? So standard deviation, we have to go to variance. We have to go to variance. Do not add standard deviations. Don't do it, okay? Add variance. So if you're given standard deviation and standard deviation, you can actually just square the numbers, add them, and then take the square root, okay? Back up and show you what I mean. Back. So right here, we're given standard deviations. If we try to add these, we're going to get a number way too big, okay? But if we square this number and square this number, then add them, take the square root of that, then I'll have standard deviation, okay? So that's kind of what that looks like. Let's look at an example. Let me go bloop, 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 bloop. All right, you ready? Okay. Oh, I should say, I'm doing all this from an addition standpoint. Works the exact same way with subtraction, okay? So if I'm wanting to subtract two random variables, I can just subtract the means and I'll get to the answer. But with standard deviation, you're still adding. You're still adding. The way you find, with random variables, the way you find standard deviation is square, square, add square root. Square, square, add square root. No matter whether you're adding or subtracting, that's your process, okay? So a nationwide exam consists of multiple choice section and free response section. For each section, the mean and standard deviation reported. So the multiple choice mean is a 38 with a standard deviation of 6 points. The free response is a 30 with a standard deviation of 7 points. The test score is computed by adding the multiple choice and free response. What is the mean and standard deviation? Okay, so if I want to talk about the mean of this, I can just say mean plus mean. Okay, well, the mean score on this test is a 68. Okay, the mean test on this score is a 68. If I want to talk about the standard deviation, I cannot say 6 plus 7, the standard deviation is 13, because it'll be wrong. Okay, in order to get the standard deviation, we say 6 squared and 7 squared. So 36 plus 49, 36 plus 49 is 85, and the square root of 85 is 9.2. Square, square, add square root. Square, square, add square root. Okay? Simple as that. Simple as that. So we've got our mean and standard deviation of, I'm going to assume percent. I'm going to say percent, even though it's not given, so I'm not 100% sure, but mean of 68% and a standard deviation of 9.21%. Okay? So kind of remember what that means too, like the average or the expected score on the test is 68%, but that score varies by about 9% on either side of it. Okay, so 68% of the population would score within 9 percentage points of 68. So that's what that means. Okay, so far we've concentrated on finding the rules for means and variances of random variables. So that's kind of what we just talked about. If it's normally distributed, we can use mean and standard deviation to compute probability. So we have talked about this before. You're going to need to go to your calculator. An important fact about normal random variables is that any sum or difference of independent normal variable is also normally distributed, right? So if it is, even if it's a random variable, if it's normal, we can use all of our normal distribution things that we have. So, you know, that's that normal distribution stuff in your calculadora with the normal curve. Okay, so Mr. Starnes likes between, what is this? Did a terrible job. Mr. Starnes likes between 8.5 and 9 grams of sugar in his hot tea. Suppose the amount of sugar in a randomly selected packet follows a normal distribution with 2.17 grams and a standard deviation of 0.08 grams. If Mr. Starnes selects 4 packets at random, what is the probability his tea will taste right? So what does he like? Between 8.5 and 9 grams of sugar. So we got to keep that in mind because that's what's going to make his tea taste right. Okay. So he's selecting 4 packets at random. Each packet has a mean of 2.71 grams and a standard deviation of 0.08 grams. So really think about what are we doing here? We're adding packets of sugar together. okay? So we're gonna say T is the probability of packet one, or excuse me, the distribution of packet 1, 2, 3, and 4, okay? And we're trying to find the probability of between 8.5 and 9 grams of sugar. So kind of keeping that in mind here. In order to find this probability, and maybe I should have backtracked this a little bit, but in order to find this probability, then we want to get on a normal curve. What is mean? What is standard deviation? So I can go to the normal distribution in the calculator and calculate it, okay? So if I want to find mean, I'm going to just add up all my means. Remember, it's perfectly fine to just add up all your means. So we would expect 4 packets of sugar to have 8.68 grams of sugar, okay? We would expect 4 packets of sugar to have about 8.68 grams of sugar, which is good, right? Because that's what he wants. The problem is there's some variability in how much sugar is in each pack. Because if all of them were 0.8 gram low, it wouldn't taste right. Or if all of them were 0.08 gram high, it probably wouldn't taste right. All right, so now we have to find standard deviation. So to find standard deviation, remember, we can't just add. We can't just add. We gotta go to variance. So we square, 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 square. Then we add. We get 0.025. And we get a standard deviation, which I don't know why he's floating over there, of 0.16. So my standard deviation for the sum of all those packets, the standard deviation for the sum of all those packets is about 0.16 grams, okay? So now I can draw a normal curve. I can draw a normal curve now. It's gonna look something like this, okay? So you've got 8.68 in the middle, and then you're adding 0.16, 0.16, 0.16, subtracting 0.16, 0.16, 0.16, and we want somewhere between, or we want the probability between 8.5 and 9 grams. So look where that falls. Where that falls on the graph. Go to your calculator. Normal distribution. Lower limit 8.5. Upper limit 9. Mean 8.68. Standard deviation 0.16. If you've forgotten how to do this in the calculator, please hop on office hours or go back to that video that we posted from that Mr. Bobby made for you, okay? So the probability of his tea tasting right is about 85%. He's got about an 85% chance of his tea tasting right. I don't know why we're so focused on Mr. Stern's tea, but there it is. There it is. All right, guys, one more, and I'm just gonna put it on the screen and just talk about it because I did a terrible job with when things pop up, okay? Bob and Lawrence run a 2-person lawn care service. They have been caring for Mr. Johnson's very large yard for several years, and they have found that the time it takes Bob, ooh, hang on just a second, that is a loud train. Okay, I shut my doors and windows. It was just, I had them open because it was nice, but that train was, all right, starting over. Bob and Lawrence run a 2-person lawn care service. They have been caring for Mr. Johnson's very large lawn for several years, and they have found that the time it takes Bob to mow the lawn itself is approximately normally distributed. This is really important for them to tell us this because it's going to allow us to go to the normal curve and use that function in our calculator. It has a mean of 105 minutes and a standard deviation of 10 minutes. Meanwhile, the time it takes for Lawrence to use the edger and string trimmer to attend to details is also normally distributed with a mean of 98 minutes and a standard deviation of 15 minutes. They prefer to finish their jobs within 5 minutes of each other. What's the probability that this is going to happen? And assume that their finish times are independent. Meaning that, what? Bob's work has no impact on Lawrence, and Lawrence's work has no impact on Bob. Like Bob can do his whole job in the same amount of time, whether or not Lawrence is involved at all. Lawrence can do his job in the same time without Bob interfering at all. So Bob doesn't have to mow part of the yard before Lawrence can start. And Lawrence doesn't have to trim something before Bob can start. Does that make sense? Independent. Okay. So we're interested in finding their difference. Why are we interested in finding their difference? Well, we want them to finish within 5 minutes of each other. If they finished at the exact same time, it takes Bob 2.5 hours. It takes Lawrence 2.5 hours. I subtract them. There means that they finish at the exact same time because there's no minutes between them, right? Okay. Let's say Bob takes 2 hours and 25 minutes and Lawrence takes 2 hours and 35 minutes. Now there's 10 minutes between them, and I can just subtract them to find that 10 minutes. So this is why I'm interested in subtracting in this case, okay? So to find the mean, now why am I trying to find mean? Well, I'm trying to find a probability, and if I'm trying to find a probability of a normal distribution of random variables, that means I need mean and I need standard deviation. So I can go to the calculator, plug it into the function in the calculator and get an answer. Okay, so I need mean, standard deviation. So, are you ready? In the means, I can just subtract them. So what does it take? It normally takes Bob 105 minutes, and it normally takes Lawrence 98 minutes. And so I subtract in, it normally takes them a difference of 7 minutes. So it takes Bob a little longer than Lawrence normally. And with the mean's not looking good, right? Because the mean is 7 minutes and they want to finish within 5 minutes of each other. But remember, we got variability in their work. Let's say today Bob stops to take an extra 4 drinks of water, and so it takes him 2 minutes longer because he's taking more water breaks, okay? So we've got some variability here, and so we've got to consider our standard deviation. Now remember, with standard deviation, even though I'm subtracting them, I still am adding the variability is always added, okay? So square, add, square, add, take the square root. So standard deviation of Bob is 10 minutes. Standard deviation of Lawrence is 15 minutes. So square, add. I get 335. Take the square root, got 18.03. Okay. So that means that the mean is 7 minutes and the standard deviation is 18 minutes. They have quite a large standard deviation. Now, I want them to finish within 5 minutes of each other. 5 minutes on Bob's side or Lawrence's side, it doesn't matter. So the probability can now be between -5 and +5, right? If Bob takes longer, it's going to be positive. If Lawrence takes longer, it's going to be negative. So I go to my calculator. I go to normal distribution. My lower limit's -5. My upper limit is +5. My mean is 7. Standard deviation is 18.03. Can you imagine this in your head, this normal curve? I always like to draw it. Some people don't have any issues, but I always like to draw it. So what does it look like here? It looks like it looks like the distribution, or the probability, the chance of that occurring is about a 20% chance, okay? So I hope that makes sense. I hope that was helpful. You've got 3 Khan Academies and then 4.7 through 4.9 quiz coming to you this week. Good luck. Have a wonderful day, and I will see you on the flip side. Bye.